Curious minds. In today's lecture, we are going on a journey exploring the structure of atom. Curiosity has always been humanity's flashlight, guiding us through the unknown. And one of the biggest questions we as human beings have asked is what is everything made up of? Right? That was the question. What is everything made up of? Because as we progress, like the human life developed on this planet, the question was obvious: what is everything made up of? The answer takes us on a journey from ancient ideas to the heart of atom itself. Let's explore how it all began. So it began with this question, and this question distilled to that the universe is made up of these two things: matter and energy. Right? So some people focused on matter, like understanding what is matter made up of, how are the things arranged inside the matter, etc. What are the different states in which a matter can exist. Some people focused on the energy part, and some on the interplay or the dance between matter and energy. But in today's lecture, we will be focusing on matter itself, right? So throughout history, in different parts of world and at different times, many curious minds set out on a journey to understand this matter. But for today, we will focus on the two key figures from ancient Greece. Their name were Leucippus and his student Democritus. Democritus was a student of Leucippus, and I'm talking about 4 or 5 centuries this before Christ era, right? So they proposed a bold idea that if we keep on dividing matter like into smaller and smaller pieces, we must eventually reach a point where it cannot be divided any further. For example, you're writing with a pencil. You're using pencil. The tip of the pencil is made up of graphite, which is nothing but carbon. If you keep on dividing that graphite, ultimately there would come a point, whether you can see that with your eye or not, that is immaterial. But we are talking in terms of like if we keep on dividing, we'll reach a point that wherefrom if you divide it further, it would no more be the carbon atom, it would be something else, right? So they proposed this idea that if we keep dividing matter into smaller and smaller pieces, we must eventually reach a point where it cannot be divided any further, and these fundamental particles, they name them as atomos, which is a Greek word for indivisible, right? However, as usual, not everyone agreed. Philosophers like Aristotle and Plato believed that the matter was not made up of indivisible particles, but it is a kind of blend of elements like earth, water, fire, etc. Now, for centuries, Aristotle's view dominated. Now I'm fast forwarding this story to come to 16th century. Okay, so which is a time of rapid industrial growth, scientific curiosity, as well as bold experimentation. It was in this period that three key scientific laws emerged based on the observations, each pushing the human race or humanity closer to accepting the atomic nature of matter. And those three laws were law of conservation of mass, second is law of definite proportions, right? And third is law of multiple proportions, right? Now we'll delve into these laws and see how they reinforce the idea of the presence of atoms in matter. Okay, law of conservation of mass says that during a chemical reaction, the mass of the reactants is equals to the mass of products. Like all the reactants, they change into the products, or in other words, we will say matter can neither be created nor be destroyed. Neither be created nor be destroyed. They just change from one form to another, like there's just a rearrangement, right? So let's see that with an example. Like if you have sodium, solid sodium, you combine this with chlorine. Under suitable conditions, you get sodium chloride, right? I'm not writing the what are the conditions for that. Suppose you have taken x1 grams of sodium combined with x2 grams of chlorine, then the mass of sodium chloride would be x1 plus x2 grams. That is, the total mass is conserved, right? So from this, they proposed that there is just the rearrangement of the atoms, right? So this law was given in 1789 by Lavoisier, right? So if I represent sodium with these dots, sodium atoms, okay, this is sodium, solid sodium, then chlorine, suppose I take this one, okay, I take this is the chlorine. So when the reaction takes place, what happens is, so you have sodium, 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 and now the chlorine is here, 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 here. So it's just the rearrangement of the things. This is how they envisioned it, right? How is this giving us an idea that the matter is composed of atoms? So since the matter is made up of tiny stable building blocks that rearrange but don't vanish, as I have picturized here, so that gives us the idea that the matter is composed of atoms. Now we're coming for the second law, which is the law of definite proportions. So let's understand this law with the example of water molecules. So this was given in 1797 by Joseph Proust, right? So try to understand with the example of a water molecule. So this law states that whether you take water from pond or from river or from any other source, or you synthesize that in the lab, it is always going to be composed of 2 grams of hydrogen and 16 grams of oxygen, right? Or 2 atoms of hydrogen, 1 atom of oxygen. This is another way of saying the thing, since we now know water is represented as H2O, right? So if matter was a random mixture, these ratios could have varied. But the consistent ratio hints that the compound is made up of fixed combination of the atoms. It is just like saying a molecule of water always has 2 hydrogen, 1 oxygen. That is, they combine in fixed, a kind of recipe. They always combine those fixed recipes. Suppose it is ammonium, okay? You synthesize it, or it is produced as a byproduct in some reaction. It is always going to have 1 atom of nitrogen and 3 atoms of hydrogen, right? Or 14 grams of nitrogen and 3 grams of hydrogen, right? So what is the statement? All samples of a given compound, irrespective of its source or the way it is synthesized, would have the same proportion of their constituent elements. What are the constituent elements in water? Hydrogen and oxygen. They would always be present in this ratio. And if they are present in this ratio, it means they are composed of some chunks which have the definite whole numbers. It's nowhere like 1.5 or something, and it's not changing. So that is the law of definite proportion. It gives us indirectly the hint for the presence of atoms. Now we are going for law of multiple proportions. Law of multiple proportions. What does this? states, this was given by John Dalton in 1804. Let's try to understand this with example of water and hydrogen peroxide. Hydrogen peroxide, right? Water is H2O, hydrogen peroxide is H2O2. Now, if you see that in case of water, you have, for every water molecule is formed of, like, has 2 atoms of hydrogen and 1 atom of oxygen. 2 grams of hydrogen and 16 grams oxygen, right? And if you take 18 grams of water, this is what is the ratio. For this one, it is 2 grams and 32 grams because the atomic mass for this one is 16. So 16 times 2 is 32, right? Now, what is the ratio here? For 1 gram of hydrogen, this would be 8 grams. For 1 gram of hydrogen, this would be 16 grams. Now, if you look at the ratio of how much 1 gram of hydrogen combines with oxygen, it is combining with 8 grams to form water, with 16 grams to form hydrogen peroxide. And what is the simple whole number ratio between them? It is 1:2, right? So if I fix the amount of hydrogen and see with how much of the oxygen it combines to form water and hydrogen peroxide, then the ratio of those numbers, like for oxygen in water, for oxygen in hydrogen peroxide, this ratio would always be a whole number, right? So if 2 elements form 2 different compounds, the masses of one of the elements that combines with 1 gram of the other element can be expressed as a simple small whole number ratio, right? It means matter isn't combined in arbitrary amount, but in discrete chunks. That's why the ratio is like 1:2. So there are discrete chunks, okay, 1, 2, 3. So that's what we see nowadays. We now know the formula and all that, that 1 oxygen, 2 oxygens, right? So this strongly implies that atoms are indivisible units which combine in specific ratios, and you can't have 1.5 atoms, for example, so that the masses combine in neat whole numbers. So you understand the laws, and these laws, they were combined later. They formed the foundation of Dalton's atomic theory and set the stage of our understanding about the atoms. So now I would discuss the postulates of atomic theory of Dalton. So Dalton's atomic theory. So there are mainly 4 postulates. So first is that each element is composed of tiny indestructible particles which are called atoms. Every element is composed of atoms, and those atoms are indivisible, right? Elements are composed of atoms which are indivisible. Second is all atoms of a given element have the same mass and same physical and chemical properties. So mass and physical and chemical properties. What does it mean? It means if I take I'm talking suppose about nitrogen, then all the atoms of nitrogen would have the same mass, okay? And all atoms of nitrogen would have the same physical as well as chemical properties, right? And they would be different from the mass of oxygen. So the mass of atoms of oxygen would be the same, and their physical and chemical properties would be the same. So you choose any element, it would have its unique mass, atomic mass, and unique physical and chemical properties, and all the atoms of that particular element will have the same things, same mass, same physical properties and chemical properties, right? Now this was a postulate of Dalton, but with our in today's scenario, we know that this is not true as far as this mass thing is concerned. We know that we have isotopes, that is the atoms of same element who have different mass numbers, different masses, okay? So we can have, like for oxygen, we have oxygen 16, oxygen 18. This is because number of neutrons is different. And we will discuss this in the subsequent videos in detail, right? Number 3 postulate is atoms combine in simple whole number ratio to form compounds. We have already seen in the law of definite proportion. Atoms of one element cannot change into the atoms of other elements, like nitrogen cannot change into oxygen in a chemical reaction. Atoms of one element cannot change into the atoms of another element. In a chemical reactions, the atoms only change the way they are arranged, or the way they are bound to the other atoms, right? So this was the postulate. But uh, in today's scenario, we know that atoms can be changed from like nitrogen to oxygen. Like there are nuclear reactions which changes the atoms of a particular element into another element, right? So this was all in 1800, early 1800s, 1808 this theory came. So this was about the Dalton's theory. So now we have seen how the idea of atom first took shape, like what was the history behind that. So now get ready to dive deeper as we explore the different models in the subsequent videos. And those models are going to change your perception about atom forever. So we'll be discussing in the subsequent videos the J.J. Thomson's experiment, cathode ray tube experiment. Then we will study Rutherford's model, Rutherford's gold foil experiment, and then Bohr's model, and ultimately we'll be going for the quantum mechanical model of atom. If you like this material, please subscribe to my channel. Thank you.